Hello friends, today we'll discuss about a very special category of three-phase converters which is known as a three-phase half-wave converter or popularly known as three-pulse converter. We'll try to find out the various waveforms at different firing angles and ultimately we'll derive an expression for the output, average and RMS value of the voltages. So it is a typical three-phase half-wave converter. The various components of this converter are as shown in this figure. This inside this circle is a star connected three-phase supply. It is a three-phase alternator and there are three thyristors. Thyristor T1, T2 and T3 are connected in series to the each coil of this three-phase supply, and of course a load is ultimately connected between neutral and these switching thyristors T1, T2 and T3. So other circuits required in these kind of setup is of course a gate triggering circuit, because we are going to use thyristor as a control rectifier. So proper control on its on and off operation will be with the help of these firing pulses which will be applied on the gate of these thyristors. But ultimately we'll have to design some kind of symmetrical switching whenever we are going to operate these thyristors simultaneously or sequentially. So here we'll start. We'll have this circuit diagram, and based upon this we'll try to generate the vector diagram of these three-phase supply. VAN representing a vector of phase A, similarly of phase B and similarly of phase Z, and we are applying a symmetrical phase sequence. That's why the phase angle difference between each is 120 degrees. Now the important thing is we are going to apply either negative sequence or maybe positive sequence. Formulate some logic or some basic rules. These basic rules will be: the thyristor with highest forward biased voltage will have the priority to conduct or trigger first. We'll understand this term. Thyristor with highest forward biased voltage, like from this waveforms or these waveforms of say phase A, this red representing the waveform corresponding to phase A with respect to neutral. This blue is representing phase B corresponding to neutral, and similarly this yellow representing phase C corresponding to neutral. Now thyristor with highest forward bias voltage with respect to the ground, this is the ground axis 0 degree or 0 volt axis. Above to this ground all the voltages are positive, and below this ground level is all the voltages are negative. So if you are going to find out the highest forward bias voltage, that voltage from this starting point till this line, dotted line, the voltage C, voltage of the C phase is having highest value in positive direction, but this duration is very small. So considering this, our starting point will be from this 30 degree instant, that is pi by 6. So we will start from now onward, we will start our operations from this pi by 6 instant. It is our initial starting instant, or it is our reference whenever we are going to find out waveforms, or we'll try to calculate values of voltages. Our starting point in case of three-phase waveforms will be always and always this pi by 6 duration. It is our starting point, reference, or maybe our 0 you can say. So initially we will trigger the thyristor corresponding to this phase, and thyristor connected to this phase, it is phase A, is nothing but T1. So T1 will be trigger over here. So from this point up to this point, T1 is having highest forward bias voltage or positive voltage. Second thing is each thyristor will conduct for a duration of 120 degree or 2 pi by 3 radians. Before this we should understand the various important point of this waveform. This representing pi by 6, this point representing pi by 3, this is representing pi by 3, and you know that this maximum or the peak of a sine wave representing pi by 2, and this crossover of this blue wave representing 2 pi by 3, that is 120 degree eventually. And this crossover of blue and red, it is representing 150, that is 5 pi by 6. And finally the complete first positive half of this red wave is representing this point as pi. So the durations are pi by 6, pi by 3, 2 pi by 3. Of course, between pi by 3 and 2 pi by 3 there is pi by 2, 5 by 6 and pi. So we'll trigger thyristor T1 at this instant, and this will continuously trigger corresponding to the second point up to this 120 degree duration, that is of equal to 2 pi by 3. So this complete duration of conduction of thyristor T1 will be equal to 2 pi by 3 or 120 degrees. After this, thyristor T2 will be triggered, and after complete conduction of thyristor T2, that is of equal to 120 degree, again T3 will be triggered. So clearly this is the firing sequence. So a complete cycle of 120 plus 120 plus 120, that is equal to 360 degree will be achieved. So in complete duration of 360 degree, there are 3 pulses of output voltages. That is why this kind of converter is known as 3-pulse converter. It is the theory behind this. Now we'll try to observe the operation of this converter with pure resistive load. So over here the load connected is pure resistive. Fine. And the property of resistance is its voltage V0 and the corresponding current I0, they both are in the same phase. Fine. So we'll trigger thyristor T1. So obviously coil A of the alternator will be connected to our load. Load current will start to flow, and finally this terminated towards the neutral point. This is how the current will flow from phase A through load to the neutral point of our supply. So our starting point will be pi by 6, where thyristor T1 will be triggered, and pi by 6 plus 2 pi by 3, that means thyristor T1 will be conduct up till 5 pi by 6. Whenever you are going to add these two, you will get 5 pi by 6, or simply 30 plus 120 equal to 150. So at 5 pi by 6, that is 150, T2 will be triggered, and then after 120 of this, that is somewhere around 270 degrees, T3 will be triggered. So this is how we are going to operate. So the total output voltage will be nothing but the voltage available between these two durations corresponding to operation of T1, similarly corresponding to the operation of T2, and in the similar fashion of T3. So we'll get 3 pulses, 3 different pulses, output voltages corresponding to the triggering of T1, T2 and T3. So this envelope will be copied, and output voltage V0 can be plotted by simply copying this envelope of Vn, Vbn and Vcn. So ultimately, so far we achieved 3 pulses, duration from this point pi by 6 up to this point, and this complete duration will be equal to 360 degree, that is equal to 2 pi. So in a total duration of 2 pi, there are 3 pulses: pulse 1, pulse 2 and pulse number 3. That is what is known as the 3-pulse converter. So here the firing angle considered in this case will be equal to 0 degree, and I have already discussed that alpha equal to 0 degree is nothing but pi by 6 instant of a 3-phase waveform. So it is our starting or reference point. Reference point or starting point of any 3-phase waveform corresponding to firing is pi by 6. Now we will take more values of firing angle. Alpha equal to 30. Alpha equal to 30 means, actually alpha equal to 30 means we are dealing with 30 plus 30, that is equal to 60. So our point of start will be 30 plus 30, that is this point, 60 degrees. We'll try to start from this point. T1 will be triggered over here, that will conduct till next firing, that is T2, and after this T3. Remember, the load is pure resistive, and remember one more condition: to turn on a thyristor in a control operation, we need forward bias voltage and gate triggering pulse, so that sufficient latching current will produce and thyristor will trigger or turn on. But to turn off a thyristor, we required the condition, that is the condition of holding current. Whenever circulating current through thyristor will fall well below the holding current, the thyristor will be automatically turned off. And in case of pure resistor, whenever voltage reduced to zero, we will assume that current will also reduce to zero, and we'll consider at that particular instant thyristor will be automatically turned off, because it is the condition ideally where circulating current through thyristor become zero. So we'll consider the ideal conditions, and when we trigger thyristor T1, the priority of T1 will be conducting till 120. But what happens from this point of triggering till 0, till when the level of voltage becomes 0, and it is the case of pure resistor, when voltage becomes 0, current will also fall to 0, and under this circumstances thyristor will be turned off. But from this point thyristor T2 will take over, so ultimately these voltage level will shoot up. So for very small duration current will be discontinued, but it will be taken over by thyristor number T2, and in the same way thyristor T3 will be triggered when the current of thyristor T2 become 0, and the same cycle continued. So we can draw the waveform of the output voltage wave. This will look like this: T1, current will discontinued, then T2, and then T3, and so on. So T1, T2, and T3. Now for same pure resistive load, now we'll take another instant of firing angle, that is alpha equal to 60 degrees. So alpha equal to 60 means eventually it is 90. It is 90. So T1 will trigger at peak of red, T2 at the peak of blue, and T3 at the peak of yellow phase. So we'll draw the envelope of wave output voltage. It will continue till 0. At instant 0, current becomes 0, thyristor will be turned off, automatically turned off, and at this point there is no thyristor which is conducting, that is neither T2 nor T3. That's why this is 0 voltage or 0 current duration. After this T2 will fired, and similar condition repeats, and then T3 will be fired. So the output voltage waveform will be bit different, and current is clearly seen discontinued or discontinuous current. Current becomes 0 means discontinuous current operation. So this is how we can draw the waveform corresponding to voltage V0 for both the cases. Now we'll cover the more important part, or the most important part, that is the operation of this same converter with RL load. And before doing this operation, we'll simply read this point. The load inductance is very large. So first of all, over here the load connected is not pure resistor, it is a RL load. It can be a motor RL load or maybe RLE load. So the inductance is sufficiently large so that the continuity of load current will maintain from the supply towards the load, even though the reverse bias voltage appeared across the thyristor. Remember this thing again. that thyristor can be turned off only when the current through thyristor fall below the holding current. So under this condition, why this particular point is important, we know that for a pure inductor the voltage and current lags by a phase angle of 90 degree. Current lags behind the voltage by an angle of 90 degree. That means we can say when voltage is maximum, current is eventually zero under ideal condition, and when voltage becomes zero, current reach to its maximum value. So we'll consider that case, and simply we'll try to find out what is the main difference between the R and RL load. So at alpha equal to 60, when we trigger thyristor T1, and after that T2, and after that T3, all the rules remain same, that is all the thyristor will conduct for a duration of 120 each. So when T1 is triggered, what happens? Current will flow, supply connect to the load, that is RL load, but at this instant of 0, although thyristor T2 is not triggered, but what happened? Because it is an inductive load, at this point current flowing through thyristor T1 is sufficiently large, so it keeps on conducting till next triggering, that is of T2. At this point when T2 triggered, the conducting path will be between coil B through thyristor T2 towards load. This operation complete, and after this same cycle repeat like T1, and then T3 triggered, and then repetition start. So the waveform corresponding to the RL load is bit different as compared to R, because in this particular case there is a conduction in the negative half also, because of the nature of the inductive load, that current continues to flow through the load even though the voltage becomes zero. So the waveforms are a bit different. However, the total conducting duration of a thyristor remain 2 pi by 3 duration for each thyristor. For RL load, for alpha equal to 30, this is the waveform. For alpha equal to 60, we have already discussed, these are the output, and for alpha equal to 90, the output corresponding to this pink envelope are clearly seen. So T1 is triggered at alpha equal to 90, means 90 plus 30, that is equal to 120. So it is 120 degree instant, where first of all thyristor T1 is triggered, and then after 120 thyristor T2 is triggered, and then thyristor T3 is triggered. So these are the envelope of voltage waves corresponding to T1. These are the voltages corresponding to T2. These are the voltages, and corresponding to T3. So equal conduction, equal amount of conduction in positive half as well as in the negative half. Now the next part is we'll try to find out the expression of average and RMS value of output voltage. This is the waveform basically for alpha equal to 90, but it's starting from 30. So pi by 6 plus alpha till 5 pi by 6 plus alpha is the conduction duration of T1, and at that point T2 is triggered. Similarly, from 5 pi by 6 plus alpha up till 7 pi by 6 plus alpha, T2 is conducting, and 7 pi by 6 plus alpha where T3 is triggered. So each thyristor conduct for a duration of 2 pi by 3 radians. So we'll try to find out average value. That average value, or VDC, is equal to integration of a voltage wave of a particular phase. For simplicity, we'll take Vm sin omega t with respect to t omega t. The starting limit will be from pi by 6 plus alpha, last limit of T1 5 pi by 6 plus alpha, because all cycles are identical, that's why we'll take only one case, and the duration of one cycle in this particular case when T1 is triggered, or maybe T2 is triggered, or maybe T3 is triggered, is 1 upon 2 pi by 3, 1 upon 2 pi by 3. So this is how we find out the average value. So VDC is 3 Vm upon 2 pi, and it is minus cos omega t. The limit is pi by 6 plus alpha to 5 pi by 6 plus alpha. So after solving, after putting down these limits, you will have to do mathematical calculation in between. I am simply writing down the final result. It is like this: 3 root 3 Vm upon 2 pi cos alpha, where you know that it is for a star connected supply, root 3 Vm representing the line voltage. So it can also be written as 3 times V line maximum upon 2 pi cos alpha. The maximum value of this DC voltage is 3 root 3 V upon 2 pi. So we can also find out the normalized voltage, which is the ratio of VDC with respect to VDC maximum, and which will comes out as cos alpha. So the governing factor is cos alpha, or firing angle. So we can play with the voltages, with the voltage waveforms, by simply playing the firing angle of thyristor. So these kind of converters are used in industry. They're having better output in terms of voltages, currents, or power as compared to a single phase counterpart. So RMS value you will have to find out by your own. I'm simply giving you the expression. It is similar: 2 pi by 3 or 3 upon 2 pi Vm square sin square omega t. Limit of integration remains same. This 1 by 2 representing square root, because whenever we are going to take RMS value, the procedure is bit reversed. That is, first of all we will take the square of the given voltage wave, then we'll take mean, and then we'll take root. So this is how we can find out RMS value, and you will have to verify that RMS value is given by root 3 Vm bracket 1 by 6 plus root 3 upon 8 pi cos 2 alpha. So this is how we can simply find out voltage and currents in case of 3 pulse converter. So stay tuned for more in power electronics, but please subscribe and like my channel. Thank you so much.